So the first problem that we will be solving is as given here. We have to determine the dot product, determine the dot product between ax cap, ay cap, az cap and a rho cap, a phi cap, az cap. In fact, it must be determining the dot products. So the question is to find out the dot product between each of these three unit vectors which are in the Cartesian coordinate system with each of these unit vectors which are defined in the cylindrical coordinate system. So as you know, arrow is directed outwards from the z-axis and a phi cap is the unit vector which goes around the z-axis, and az cap is the one which is towards the z-axis, which is parallel to the z-axis. So we have to find out the dot product between. So we are going to get totally 9 dot products. This into this, that is into means dot product, this dot this dot this dot this. Similarly, ay cap dot this, ay cap dot a phi cap, ay cap dot az cap, and az cap dot arrow cap, az cap dot a phi cap, and az cap dot az cap. So what we do is we will form a table and we will fill the entries in this table one by one. So a dot here to mean that what I am about to do here is a dot product, and I will have 3 columns here and 3 rows here, and I have a row cap here, a phi cap, a z cap, and so these are the 3 unit vectors of the cylindrical coordinate system. And over here I will have ax cap, ay cap, az cap. That is the Cartesian, the unit vectors in the Cartesian coordinate system. Okay, now we will fill these 9 slots. So here I will be writing the result of ax cap dot arrow cap, and dot product, as you know, is commutative, so arrow cap dot ax cap will be the same. Okay, now for reference, I will draw a figure here. And if I choose an arbitrary point P somewhere here, say, then as you know, so let me call this as the point P. Let me write it down here. So we know that this will be a row cap at that point. That is the vector which is radially outward, a row cap, and this will be a phi cap. A phi cap is actually, it's in the form of a tangent to a circle which has its center on the z-axis, or a cylinder which has its center on the z-axis. So a phi cap will be tangential to that. And then of course az cap. Az cap. And now we will see the projection of this point here, and we, or in other words, I would say that we will take a look at this from the top. That is, we will have the z-axis like this coming out of the board, x, y, and then the point P would be appearing like, say, like this, point P, and a rho cap would be this, a rho cap would be that, a phi cap will be this, perpendicular to a rho cap, and az cap will be out of the board. Now I will also plot ax cap here because we have to take the dot product here. Now ax cap is a unit vector which is parallel to the x-axis. And remember, these unit vectors are free vectors, so we can position them anywhere in the xy plane. When I show ax cap, I can position it anywhere on the xy plane. I need not necessarily have it aligned with the x-axis. And a y cap would be this. And you know that from the definition of the cylindrical coordinate systems, we know that this angle will be phi. Now, ax cap dot a rho cap, when I find out, I get ax cap dot a rho cap is equal to magnitude of ax into magnitude of a rho, which is 1 each, into cosine of the angle between them. The angle between them is phi. So the result of ax cap dot a rho cap is cos phi, and we can enter it here, cos phi. So that's how we are going to fill this table. Now we see that this angle is 90 minus phi, because this is 90, this is phi, so it is 90 minus phi. So a rho, or rather ay dot a rho cap will be magnitude of ay into magnitude of a rho, which is 1 each, into cosine of the angle between them. Angle between them is 90 minus phi. So cos 90 minus phi gives us sin phi. So cos 90 minus phi is cos 90 cos phi, which is 0, plus sin 90 sin phi, which gives us sin phi. Okay, so that means that ay dot a rho gives us sin phi. Okay, now we move on to finding out what is ax dot a phi, ax cap dot a phi cap. So for that, we notice that this angle being 90, this angle being 90, and this being 90 minus phi, this has to be phi. So that is phi. So that when you add these two, you get 90, which means that the angle between ax cap and a phi cap is phi plus 90 minus phi plus phi, which gives 90 plus phi, which is quite obvious from this figure as well, because this is 90 and this is phi. So 90 plus phi is the angle between ax cap and a phi cap. So ax cap dot a phi cap is equal to, magnitude is 1 each, so cosine of the angle between them, which is cos 90 plus phi, that gives minus sin phi. So here I will have minus sine phi, because this is ax cap dot a phi cap, and this will be a y cap dot a phi cap. Now this angle is phi between ay cap and a phi cap. So the dot product will be magnitude is 1 each. So cosine of the angle between them, which is cos phi. So this becomes cos phi. And now what remains is ax dot az, which is 0, as you know, because they are perpendicular to each other. Ay dot az is also 0. Az dot a rho is 0 because a rho is this, az is out of the board. So az dot a rho perpendicular to each other, so 0. Az dot a phi, again if you see a phi is there and az is here out of the board, so the dot product is 0. And az dot az, we know the result is 1 because the magnitude is 1 each, and essentially you are taking the dot product of a unit vector with itself, the result will be 1. So this is the solution to this problem. It's actually more of a derivation, not a numerical problem, but still this table will be quite helpful when we solve the remaining problems which we will be discussing. Now we move on to the second problem. So here the second problem is express the unit vector, express the unit vector, express the unit vector which points from z equal to h on the z-axis, which points from z is equal to h on the z-axis towards the point rho phi 0, an arbitrary point rho phi 0, and this is of course in cylindrical coordinates. So express the unit vector which points from z is equal to h on the z-axis to rho phi 0. So let's draw a picture, because a picture will be always helpful. Now the given point, the first point is z is equal to h. So if I say this is, say this is h, then this point is z equal to h. So we have to find out the unit vector from here to rho phi 0. Now rho phi 0, z is 0, z axis, z coordinate is 0, means we are on the xy plane and rho and phi can be any value. So for my convenience, I'll just take it as a point somewhere here on the xy plane. It's on the xy plane. So this is rho, this is phi. So from here to here, that means we have to find out the unit vector. We have to express the unit vector which points from this to this. That means we have to basically find the vector which points from here to here and divide that vector by its magnitude to get the unit vector which we are looking for. Okay, so here we see that we can identify a position vector like this related to this point which will be rho arrow cap. This is rho arrow cap, and we have a vector, the vector representation of this, that means a position vector of this point will be h az cap. Now, our problem is basically, if you look at this, you have one of our problem is now, if you look at it from this angle, we have vector rho arrow cap and h az cap. We need to find this vector. We need to find this vector. And we can easily write that this vector is rho arrow cap minus h az cap. You can see that this vector is rho arrow cap minus h az cap. So we can even look at it like, so minus h az cap will be this, and this vector is nothing but, if you use the parallelogram law, you see that it's nothing but rho arrow cap minus h az cap, because this is minus h az cap. Anyhow, one need not think in that manner. It's quite obvious from this that this vector is, so this vector is nothing but rho arrow cap minus h az cap, and we have to now normalize it in the, because we have to find the unit vector from here to here. So all that we have to do is rho arrow cap minus h az cap by square root of rho square plus h square. This is the vector we are looking for. This is the unit vector that we are looking for. Now we move on to the third problem. So we have to find the distance between, the third problem is find the distance between m5 3 pi by 2 0, and so m is the point defined by phi 3 pi by 2 0. It's in the cylindrical coordinates, and the point n, which is identified by the coordinates 5 pi by 2 10, and these are given in cylindrical coordinates. Okay. So again, let's draw a figure x, y, z. Let's roughly mark this: -1, -2, -3, -4, -5. This is the y-axis, negative side of the y-axis. 1, 2, 3, 4, 5. Similarly, 1, 2, 3, 4, so on and so forth up to 10. Now the first point M has rho as equal to 5, rho is equal to 5, not 5, 5, rho is equal to 5, and phi is 3 pi by 2. This is because phi starts from here, 1 pi by 2, 2 pi by 2, 3 pi by 2. That means the point M is lying on the YZ plane, especially on the negative side of the y-axis, on the YZ plane, on the negative side of the y-axis, because the angle is 3 pi by 2. This is 1 pi by 2, 2 pi by 2, you reach this side, and then 3 pi by 2 you reach on the, you are on the YZ plane on the negative side of the y-axis. and rho being 5 and z being 0, we could locate that point to be this. So this is m. So you can see that the coordinate of this is rho is equal to 5, phi is 3 pi by 2 and z is 0. And the other point is similarly we see it's rho is equal to 5, phi is pi by 2. That means you are again on the yz plane, but now on the positive side of the y-axis, because phi is pi by 2, we are on the yz plane on the positive side of the y-axis. Rho is equal to 5, z equal to 10. So this is the point. This is the point, and you can see that it has rho as equal to 5, rho is 5, phi is pi by 2 and z is 10. Now we have to find the distance between these 2 points, that's all. And the distance between these 2 points, it's a straight line. The way I draw, it's too smooth. It's a straight line. So this distance we have to find out, which you can easily find out from this being a right angle triangle. We know that the distance is equal to 10 square, because this is 5, this is 5, so it is 10 square. This is 10 plus 10 square under root, that gives square root of 200. So many units, that's the distance, square root of 200. One can also solve this by using the Cartesian coordinate system. It's just a roundabout, not a roundabout, it's a slightly longer method. I can define Rm, position vector of point M, as equal to minus 5 ay cap, and I can define Rn, the position vector of n. So Rm is this vector, Rn is this vector. So Rn is equal to, you can see that it is 5 ay cap plus 10 az cap. Now the vector Rmn, that is the vector from m to n, is given by Rn minus Rm, which will be 5 plus 5 ay cap plus 10 az cap. Rn is this, from that I am subtracting Rm, so 5 and 5 gets added, that's how I get this 5 plus 5, which is nothing but, of course, 10. And the magnitude of this is the distance between m and n, which, as you know, is 100 plus 100 equal to 200. Now let's take the next problem. Now here the question is, transform the vector b equal to y ax cap minus x ay cap plus z az cap into cylindrical coordinates. So this is given is a vector, in fact it's a vector field. It's given in Cartesian coordinates. We have to transform this to cylindrical coordinates. So what is given is in Cartesian coordinates, we have to transform it to cylindrical coordinates. So that means this vector has bx as equal to y, x component of this is y, y component is minus x and z component is z when it is expressed in Cartesian coordinates. We have to express the same vector as equal to b rho a rho cap plus b phi a phi cap plus b z a z cap. We should express it in cylindrical coordinates. The vector will not change. Its representation is only going to change. We have to express it in cylindrical coordinates. So to get b rho, what we need to do first is we have to take a dot product of a rho and b, that is dot arrow with b, vector b, and you can see clearly that that will give us b rho. If I take a dot product here with arrow cap, I will get b rho. This will be 0, this will be 0, because these two are perpendicular to arrow cap. So b rho, and that will be equal to b is over here. Because the vector is the same, so if I dot it with this representation or this representation, I should get b rho. If I dot any of these two with arrow cap, since the vector is the same, I should get b rho, the rho component of b. So I take arrow cap and dot it with this. When I dot it with this, I will get y arrow cap dot a phi cap, which is cos phi, as we saw in the first problem, and minus x arrow dot ay. Arrow dot ay is sin phi, and arrow dot az is 0. Arrow dot az is 0, which means that this is the rho component, but it is still in y and x, so we should get rid of that, and we know that y is equal to rho sin phi. This is the fundamental. When we study the cylindrical coordinate systems, we know that y is rho sin phi and x is rho cos phi. And we see that it is rho sin phi cos phi minus rho cos phi sin phi, which is equal to 0. This is equal to 0. So the rho component of b is 0. Now we find out the phi component by dotting vector b with a phi cap. That gives us the phi component. And let's see what we get. Y into, again, now I can, since I have explained what is y here, I can write y into a phi cap dot ax cap. A phi cap dot ax cap is minus sin phi. So minus sin phi minus, now x is rho cos phi, a phi cap dot ay cap. A phi cap dot ay cap is cos phi, and then a phi cap dot az cap is 0, and this result is minus rho, because you get minus rho. If you take common, you will get sin square phi plus cos square phi, which becomes minus rho. So a phi cap, the phi component is minus rho. And finally, az dot b is equal to, I just have to take, and that remains the same as z. Without much of explanation, I can write. This means that the vector b is equal to minus rho a phi cap, because b phi is minus rho, plus az cap z. There is no rho component. So this is the representation of this vector or vector field in the cylindrical coordinates. They are the same. Here it is expressed in Cartesian coordinates, whereas here it is expressed in cylindrical coordinates. So with this we will stop this lecture, and we will continue discussing more problems in the next lectures.